There's an entire chapter of puzzles that are coming, which is kind of fun. Actually, yeah. Yeah. It's called exponential and logarithmic functions. No, but it's a chapter of puzzles. Just wait, it'll be fun. And then there's T-proofs. That's a whole other one.
Oh, wait, what?
T-proofs?
T-proofs?
Proof.
Oh, no.
Okay.
Wait, did you say proof?
We're done. So, input, output.
Oh my lord.
Input, output. Right? A step function is a function for which, if I put in 0.9, it would give me out 0. If I put in 0.75, it would give me out 0. If I put in 2.1, it would give me 2. If I put in 3.9, it would give me 3. It's a function such that, basically, the decimals don't matter. And you always round down. Think about it. I'm going to give everyone the entire class period to think about something in real life that acts or needs or would necessitate a step function to model it. Let me do this real quick. The spacing is kind of awkwardly off. I apologize. Okay, back to the beginning. I asked you guys a question in the very beginning, and the question in the very beginning was, hey, if something is a parent, it must have kids, right?
Yes.
Or theoretically. I was talking about people, but these are parent functions, which means that everything that we talk about today, if they are the parents, well, the kid must be coming. And the kids somehow come from the parents and maintain some of the characteristics of the parents and yet are usually unique. Does anybody have any idea what the kid functions would be? Or what category they would fall under? These are the parent functions. These are the kids. Transformations, translations, dilations, reflections. The kids are coming. That's section 1.7. But for right now, the parents. Before we can get the kids down, we kind of have to know the parents. So, linear, a place we've already been, right? And a place we'll probably be a few more times. But for right now, linear is a function that can be written. Let's just do like the most common forms. Is that okay?
Yeah.
I know there. We have slope, intercept, and we have point slope. Which one did I say was more important for calculus?
Slope and point slope.
No, that one. Okay.
What is that?
Point slope. Remember that for lines, their slope is constant. Let me just say constant slope. And remember what we talked about at the end of chapter 1a was rates of change, right? So constant slope, and slope is another way of saying choking on my protein. Rate of change. Protein. He does not hear me well today.
So that's
So constant slope, aka constant rate of change. And how do we find slopes or rates of change? Can I do the snazzy f of x2 minus? Can you guys finish?
x1 over x2 minus x1.
Champs. Which is a snazzy way of saying y2 minus y1 over x2 minus x1. Snazzy function notation. Confused a few of you. Average rate of change. Okay. But lines. With any, I shouldn't say normal. Normal actually means something in math. It means perpendicular. Oh, I know. It's a little bit confusing. Regular. What's another word for normal? Regular. Basic? Sure.
Basic.
Most basic or simple lines have a slope, right? Now, it could be an uphill slope. This would be where m is greater than 0. Could have a downhill slope, right, where m is less than 0. Increasing line, decreasing line. Positive slope, negative slope. But what slope does a vertical line have again?
None.
Oh, none.
Is it none or is it?
Oh, no, that one's 0. No, that one's
Why?
that one's 0.
This one's 0?
Yeah, that one's 0, and then the vertical.
So this could be written as y equals 0x plus b, otherwise known as just y equals b. Oh, hey, like the constant function.
Yeah,
Y equals c is a flat line.
Undefined, right?
Yeah, because if you ski that, you're going to be undefined, right?
Oh, x equals.
It's technically infinite. It's technically an infinite slope. Talked about that back in the day. So it gets steeper and steeper and steeper and steeper and forever approaching infinity. The two most basic parent lines, or the strange category of special lines, is y equals c and then y equals x. Y equals c and y equals x. Y equals c, just a normal flat line at, now this one would be like what, 1.3, 1.4? Nah, probably 1.3. But they're just trying to make it general, like, okay, y equals c is going to be at whatever the constant is, whether it's 2 or -2, that's a flat line. And so the identity function y equals x, well, if that's y equals c, if that's y equals x, then who's that again?
X equals.
Yeah, x equals c, or let's do d, it'll be a different constant. But yeah, remember x equals is straight up and down, y equals is a horizontal. And this is silly. It's my way of remembering it. Sometimes it helps and sometimes it doesn't. If I were to give you something like graph x equals 7, wouldn't you have to go to the 7th tick mark on the x-axis? Yes. Wouldn't that make sense? Now, some of you are like, well, what are my y's? What's my function? But still, you would go to x equals 7. What's there? What kind of tick mark?
Vertical.
Vertical. Can't you just extend the 7 and be like, yeah, he does. There it is. Well, if you just go to the 7th tick mark on the x-axis, of course that's x equals 7. And if I was to do something like, hey, y equals -2, wouldn't you go to the -2 tick mark on the y-axis? Right? It's a horizontal line. Yeah, he does. There he is. For some reason, this has always been such a complicated issue of how to graph like y equals a constant or x equals a constant. Guys, it really is just the tick mark extended. Or at least the sound is right. Okay, let's move on. What's next? Squaring, otherwise known as the quadratic. Now, the parent function is just plain old boring y equals x squared. The parent function is plain old boring y equals x squared. What are some things that we know about this? It is a parabola, true? Parabola. Sounds like a virus. Everyone of that. Parabola. Parabola. Every parabola has, well, the parent function
we're supposed to be right.
has a minimum, I'm getting distracted. Thank you, I appreciate it. Minimum. Oh dear. At the vertex. Minimum at the vertex. The parent function has a minimum at the vertex, and specifically the vertex is at the origin, true? Right. Once we get beyond lines, it gets a bit more complicated to graph, because lines say give me 2 points, any 2 points, and then connect. So lines are easy. It's like, even if when it's a weird transformed line, it's like, give me the intercept, and then just rise over run. Boop, boop, done. But all these other functions are a bit more complicated when transformations occur. So, we want to remember things like, hey, a parabola, any quadratic has a vertex somewhere. It starts at the origin, but maybe it gets shifted around, moved around at somewhere. Yes, it has symmetry, in that it is symmetric. Not at, I apologize, about. Now, here's the struggle. The parent function is symmetric about the y-axis, right? The parent function is symmetric about the y-axis, but as soon as this shifts, it won't be anymore. It won't be even. It won't have y-axis symmetry. So it's called the axis, yeah, it's kind of silly. Symmetric about the axis of symmetry. Oh well. But every parabola does have an axis of symmetry, does have an x equal line. Now here's, remember how I said this was tricky a second ago? X equals 0 is where the parent function has its axis of symmetry. But didn't I say a second ago the y-axis? I did. People get confused, like it's the y-axis, it's y equals 0. No, it's not. Whose tick mark got extended?
X's.
X's, not y's. What would y equals 0 be? The other one. But it's called the y-axis. I know, because that's where we put the y. Careful. The y-axis is x equals 0. Just something silly, I know. Something that everyone forgets. Okay. You guys have seen these enough though. Can I just put the standard transformed version? That's okay? I mean, I gave you a transformed line. I gave you mx plus b, which has been shifted and stretched and reflected. So technically, you have a version that you kind of memorize as far as transformations. The awkward part is this one's actually horrible to graph from. The one that's way better to graph from is one that we're going to see. That's going to be our new standard form. This one.
The other one was
Because this one, the vertex is going to be at HK.
Yeah, that one's a
Don't worry, you just need to complete the square. Okay, moving on. Before you guys all get mad. Cubic. Don't worry, today is not the complete the square day. Cubic. Cubic. Doesn't have a vertex. Doesn't have a minimum or a maximum. It kind of goes up forever, down forever. Hey, what's a way of describing up forever, down forever? What can we be talking about?
Infinite.
Hey, maybe we should have been using domain and range. All right, what's the domain of a cubic function?
all real numbers.
All real numbers, because it's going to keep extending. Now, this looks an awful lot like what we call tangent of x or tangent of theta. It looks a lot like a tangent curve. The cubic is very different, though, because he's going to forever be going out. I can plug in 2 to cubit or 10 to cubit or 100 to cubit. It's going to keep on extending. It's just going to go super high, super fast. Not the fastest thing ever, but it does go much faster than like lines, for instance. So domain, it is going to go forever left, forever right.
There's speed for math. Oh my
Calculus
God,
is called the
funny.
math of change, aka the math of rates, speeds, velocities. Yeah, that's where calculus comes from.
Oh my God. I need a chocolate.
Wait a minute. But speed is easy because it's rate of change. It's slope. It's y2 minus y1 all over x2 minus x1. That's calculus. No. That's only slopes of lines. What about the slopes of squaring functions and cubic functions and reciprocal functions and square root functions? No, they don't have slope. We never learned formulas. Not yet. Anyway.
Oh my God.
Nathaniel Brodsky. Let's go there. So, here we go. Domain range. Healthy pen. Domain range. Well.
Is that an arrow next to the line?
Thank you.
Oh, it's an element symbol. It's a little e.
Oh, I've been writing arrows.
Awkward. Okay, so there aren't vertices, but there are things that we call points. I shouldn't say points. It's only going to be one. Yeah. Point of inflection. A point of inflection. That one is at the origin for this. So that point is special. He's just not a vertex. He's not a max or a min because the function goes forever high, forever low for cubic functions. A point of inflection for the parent function is at the origin. There is symmetry, but it's not. Let's just say that the parent function has origin symmetry. Is that okay? As soon as you move it, it's going to have symmetry about the point of inflection, then it starts to get kind of weird. But for right now, for the parent function, we can say origin symmetry before it gets moved around. It does have symmetry. Point of inflection we might talk about a little bit more later, but long story short, you might be like, who the heck is that? That's the point at which concavity changes. Concavity, concave up. Concave, convex. Do you see how there's one type of curvature before and then another type of curvature after?
Yes.
Now, technically, what would you say this curvature is? Concave down or concave up? Neither. It's supposed to keep going. No. What would it be a part of? Concave down or concave up?
Up. No, because it never goes down. But if there's
But I know it doesn't finish,
Oh, then down.
but the curvature is a part of concave down, right? We'll learn more about concavity as we go, but this is technically concave down to concave up. Now you guys are so used to, no, you don't need the whole thing. It's all about how the curvature is, because concavity is actually defined by, not by being a downwards cup or an upwards cup, concave up of a cup or down like a frown. It doesn't have to be the whole thing. It has to do actually with the rates of change, the slopes, decreasing or increasing. But I'm talking about tangent lines and doing calculus, let's move on. Boop. Oh, hey, speaking of which, what's the domain and range of the squaring function? You didn't talk about it. Domain. How left, how right?
Infinite.
All real numbers.
All real numbers. Can I just stop writing the x because you guys know domain is x? Is that okay?
Yes.
Right, yeah.
Okay, but what about the range?
It's X is
Because how low?
no, Y
Oh,
is
Y
So
greater
the
than
vertex
or equal to 0.
Greater than or equal to, so could I do a closed bracket with 0 to infinity? Is that cool?
Of course.
Oh, I think.
What's the bracket?
Means including, it's at 0 as well. So it's not just skimming 0, it's actually hitting it. Otherwise known as greater than or equal to, not just greater than.
Because
We forgot to put
I thought it was in range.
Okay, square root function. So let's keep going with this guy. Domain. Wait a minute. Can't do all real numbers this time.
X is greater than or equal to 0.
X is greater than or equal to 0, so 0 to infinity, true? Range.
X is
Because how far left is 0, how far right is forever.
greater than or equal to 0.
How far low is 0, and how far high is infinity. But didn't we already know this domain thing? Because isn't there a domain problem with the square root of u? How the domain always needs to be u greater than or equal to 0, right? Wasn't that a thing? Yeah. Once upon a time. So we have to watch out for this guy. Any even-powered root, the parent function, whatever's underneath must be greater than or equal to 0, or else we get into imaginary things, and that's scary.
Oh yeah, the imaginary. That's like the.
Only one concavity, so no points of inflection. There technically is a minimum. We can't call it really a vertex, but we could call it a min. It's not quite the same type of minimum as a quadratic or as the squaring function, but that's okay. And a quick reminder that the square root of x is the exact same thing as x to the 1. Why not? Let's throw in those rational exponents while we're at it. Just a reminder. So remember there's a 1 there, and then there's a 2 there. We got it?
Yeah.
What's next? Reciprocal? Reciprocal function. 1 over x. He's a little bit more exciting for his domain and range because do you guys see any x's or y's that are illegal? Illegal. What can x not be? Anything but 0. Because what exists at 0? What do we call that?
A denominator.
What? Yes, a denominator of 0, a domain problem, but we also call the vertical asymptote.
Oh right.
Range in this one, which isn't always the case, but range, what is y not allowed to be? Because what exists there? A horizontal asymptote. That's fun. Is there a point of inflection? But I see concave down and then concave up, right? So isn't there a change? So shouldn't there be an inflection point? Because it changes?
Yeah, I got it exactly right.
Not even close.
It's literally just the reflection.
How hard is it?
There is a change in concavity, but why am I not saying an actual point where it happens? When does the change occur?
Where it doesn't touch.
At the vertical asymptote where it doesn't touch. So the vertical asymptote is a point? No, it doesn't make sense. So there is no point of inflection even though there is a change in concavity. So the change in concavity actually happens at the vertical asymptote, right? But that's not a point, so I can't say it. That's enough. Yes, I see some people who are trying to multitask. I hope they're doing it well. With test corrections, when are those corrections?
Tomorrow.
Tomorrow at the very beginning of class, and they'll let groups collaborate on any last-minute questions they weren't able to get answered on their own. Sound good?
Yeah.
So as soon as you get to class, grab out your corrections. Either you have them all and you're like, I can help, or you're like, I don't have them all. I need help. But is class time, quick group collaboration, the time to do all your corrections? No, that's called foolishness. Anyway, so if you need help, come in during lunch or after school. It's technically a meeting during lunch, but I can sneak it. Maybe period 7 or after school is better. Wait, we need one more page. 5 minutes, we got this.
Oh my god.
We got this. You have done these already this year. Focus. Let's be better than chapel. To some extent, teachers don't mind in chapel as long as it's like an appropriate disruption, but when it drags on and the speaker is literally like shh and snapping at you, that's when you just shut up. Anyway, I teach that. But still, we should work a little bit more. Now, some of us are like not bad kids, we're just talkative. You can do it. It's called maturity. Anyway, coming back.
No, that's not right.
It's a life lesson, just
No, that's not right.
We've done this already this year, haven't we?
Yes.
Remember function?
Oh, I thought you said
Yeah. Thank you. Okay. Remember function notation? How we had? I can't use I. I's imaginary. Not me, but I. J. Okay. We could do something like x is, I don't know, less than or equal to. Sure, why not? A, and then we could have A, and then x, and then maybe he's less than B, and then maybe he's, I don't know. Okay, an example. Yeah. An example of a piecewise function. Function notation in chapter 1A. Oh, I was snapping. Hey. Work better. Function notation, they were giving us f of 2, and we had to see what piece it would plug into. Remember that? Some of you got really confused, some of you were okay. Talked about it in class. Basically, long story short, we have to think about the x-axis as being maybe, okay, yeah, maybe there's the y-axis, okay. But we have to think about where A is and where B is. And anywhere to the left of A or below A is going to be whatever that B graph is. And I'm just making up something random. Hey, it's a y equals c graph. Anyway. And then we could do, like, from here to here would be like my h of x. Hey, that could be an identity function. And then we could have something like, I don't know, maybe the tail end of a cubic function. Anyway, so we have basically who knows what, but a graph that's been split into 3 parts. Maybe they connect, maybe they don't connect. Maybe they're all lines, maybe they're all sorts of different weirdness. So the problem is I can't really tell you characteristics as far as like domain or range or behavior or maximums or minimums because it totally depends on who's in there. But I can tell you 2 special examples of piecewise functions. Now the weird thing is, some of you are like, what are you talking about? We've been doing this guy since forever. Absolute value is the distance of a value from 0. 4 is 4 away from 0. Negative 4 is 4 away from 0. Maybe you didn't learn it that way, but that's technically what absolute value is. It's the magnitude of the number or the distance from 0, regardless of direction. But do you know he's actually piecewise? Because he behaves sometimes like the statement, keep it the same. He behaves sometimes, oh, keep it the same. What? Yeah, any positive number, keep it the same. Nothing changes. Plug in a 5, get out of 5. Plug in a 7, get out of 7. Plug in a 1, get out of 1. Plug in a 0.00001, get out of 0.0001. But sometimes he says, nah, I'm going to flip them. Which is weird because you're like, absolute value can never be a negative. No, but it can and must be an opposite sometimes. So if I plug in a negative 5, I need a negative 5, a positive 5. Negative 7, I need a negative 7, a positive 7. This guy is a shortcut notation for a piecewise function. And last but not least, this guy, which you're going to see with these little double brackety guys, which is kind of awkward, kind of weird. It's a little bit off because basically his way of thinking about it is always round. I don't like saying this, but it's technically kind of right. Down. I'm going to put a question mark because in homework, I bet you're going to get stuck on negative numbers rounding down. Does anyone think of a real life example?
Stop that. Hey, stop.
Parking garage.
Oh.
They charge by the hour, not the minute. Think about it. Bye, guys.